All right, so at a very basic level, zk is proving computations. And so you always think of a program that you want to prove. I'll say more about that. So you have your program here, and your program takes some inputs. I don't know, input 1, input 2, and you get some outputs. And so, yeah, is this big enough? Yeah. So usually, it's kind of hard to think about zkPs for the first time you get into it. But the way I think about it now is that it basically gives you a signature, but it's more powerful than a signature. It's a signature is a signature on some data, but here we're signing the computation or the integrity of the computation, and so we're saying this program, I don't know, program. Let's give it a name, program A. Given input 1 and input 2 actually gives this output. And that's sort of what we're signing, and we have a signature. Oh yeah, maybe I'll switch side. And then, so this is just, this is cool by itself. We get a proof of that execution, and we can say that for the verifier, it's actually faster to verify the proof than to run the program itself. But it's not all. So that's, by the way, that's close to syncness. But also, the zk comes here. You can say, OK, I don't want that input to be available in my claim, in my signature, or in my proof. I want to say, I run this program with some input that you don't know, another input, and it gave this output. And you can basically decide, and you can say, OK, I want to mask the output also, or I want to mask this output, this input here. But at some point, it's not very useful if you're masking everything. So, OK, that's basically my intro of the API. I just want to know who here understood, or can I get a hand raise? So everybody gets that? OK. So now the question is, how do we prove this thing? And when we think of programs, we think of either assembly and some very low-level stuff, or we think of high-level languages like Python and PHP and whatever. And obviously, when we think of cryptography, we think of math. And so there's going to be, I guess most of that session is going to be about how do we translate these programs into math that we can prove. And that's what I called arithmetization. We can also, the second part of that is that once you have arithmetized your program and you have actual math, there is the proving, well, I'm not going to show anything here. There's the proving the math, and that's usually called the backend when you call arithmetization the front end. And I'm not going to talk about that today. But yeah, if it's a series, I guess we can talk about that the next time or next time, depending how fast we go. So, OK, so we have programs. And as I said, there's low-level programs, so assembly, and there's high-level programs. And we sort of have these two different things. Oh, I'm gonna try that. We sort of have these two different things in the zk world as well. So we have, actually, let me backtrack that. All of the programs that I've been talking so far always end up being some sort of assembly that's run by a machine, by some bare metal. And so if you think of programs from that point of view, you either have instructions, bytecode or assembly, like some instructions that is run by a machine, or you have the program of the machine itself. And the machine can be like a bare metal machine, like actual circuits using electricity and stuff, or it could be like a fake machine, which we call virtual machines. And that's sort of the distinction I wanted to introduce. I don't know if that made sense, but basically, I wanted to sort of say that there's a circuit versus VM or VM approach, where the circuit is really like you're designing your circuits like we do in real life on ASICs or integrated chips, and you have wires, you have gates, you have other wires, other gates, and these get connected together, and you have a bunch of gates and stuff like that. Or you have people write programs that will be run by, executed by machine, and the machine itself is the circuit. Is that clear? And so, what can I say about that? So I guess in zk we have and it's always confusing. That's why I wanted to talk about that. But in zk you can also write circuits directly yourself, and it sort of looks like that, and we'll call them arithmetic circuits. Or you can write the circuits of the VM itself, and then you can run program on the VM. And I guess maybe just to enter the VM world, maybe it's not super clear for everyone, but a VM is basically, some people call it, what is it, fetch, decode, execute, I think. Fetch, decode, execute. FDE, I guess. And basically it's a loop, and every instance of the loop fetch the next instruction to run, decodes it, and then execute it. It could be like, maybe it's a VM that has a stack, so it's like, okay, what's the next instruction? The next instruction is like, add the last two elements in the stack, and then it executes, it adds the two elements from the stack, and then it adds the result into the stack. So that's what VMs are. And so usually when you see zk VMs, this is what is implemented in a zk circuit. Cool. So I guess I went through these things. All right. Is that, yeah. Anybody has any questions at this point? Yeah.
Is it worth maybe talking through the trade-offs of like you have a circuit optimized for a very specific purpose versus a VM is more generalized, and so it's easier to use, but then it's not as optimized performance-wise?
Right. Okay, so remind me, I need to repeat every question, I think, so that the mic can... But the question was, is there like an optimization trade-off between the VM approach and the circuit approach? And I would say it's the same trade-off that you have with real circuits and with real VMs, not zk circuits and zk VMs, where if you're running circuits directly, you have access to more optimizations. But it's harder, and it's a whole can of worm, and developers are usually not writing circuits directly, not even writing this assembly directly. Usually developers use higher level languages, and it's easier to write for a VM. And I don't want to get too much into the VM yet, but you can think that, okay, I'll give you some spoiler kind of thing, but I'm not going to explain why. But if you're in the VM world, it's easy to write loops that have dynamic number of iterations, or it's easy to like jumps in your program or have branches. But when you're in the circuits, it's kind of harder to write these kind of things. And I'm not going to explain why.
So is it like you're proving like the state transitions like from the input to the output, and like the proof is like that it's a valid state transition?
So I guess I'm gonna talk about that next. Like, what are we exactly proving? What are these circuits that we're?
Well, I'm not on the VM side.
Oh, on the VM side?
So is it like you give an input and an output, and like the proof is like that it's a valid state transition on the VM?
Basically, you're proving that the VM is doing this loop correctly.
Like per instruction.
And that, yeah, so every instruction is like, I guess it is a state transition, right? Like that state transition is correct in every iteration of the loop. Yeah?
You could also optimize the VM with precompiles, if I'm not mistaken.
Yeah, so if you are not running circuits directly and you're running your VM as a circuit, oops, is that important? No. Then of course you're gonna want to optimize the VM as much as you can. But that being said, you're never going to have access to the same optimizations as if you're doing circuits directly. But for complex programs, maybe it's fine because it's too hard to write circuits anyway. But yeah. Yeah?
Maybe you're going to cover this, but what's in a circuit? What's the amount of you?
So yeah, I'll talk about that next. All right. So let's look at what's in a circuit. Maybe I'll remove this. We don't care about that anymore. So, yeah, I talked about circuits with like normal gates and camera. With normal wires and gates and stuff like that. And so you can think of the same as in these arithmetic circuits, so AC. And usually the conversion that we want to do is to, if your program is in Python or like whatever, we sort of want to convert them to something that looks like an arithmetic circuit, and it will look something like, I don't know, you have a wire, but instead of like a NAND gate or AND gate or OR gate or whatever, you get arithmetic gates. So you have addition gates, maybe you can multiply it with a constant, and usually you have addition and multiplication gates. And I will state that basically any program that you can think about can be converted to these arithmetic circuits with addition and multiplication. Of course, you can't like talk to the network or like do like impure stuff, but most useful programs that are pure functions can be converted to these. That's usually not the final step. We want to convert that, depending on the proof system, to something that's more manageable. So you might have heard of things like R1CS or AIR or Plonkish or things like that. So I'll get to that next. But you can think of, and sometimes the whole arithmetic circuit is sort of ignored, but you can think of it as this is basically what we want when we translate our logical program into math. We want something like that. And actually, maybe I'll give some examples here as to how we can do that. So actually, does someone knows how I can make sure that a value is a valid bit, 0 or 1? Like if I have a value x, how can I make sure that x equals 0 or 1 using only multiplications or additions? Anybody knows? Yeah.
Square minus itself is equal to 0.
X squared minus x equals 0? Yeah, so that's the answer. I guess for me it's easier to see it like this. But yeah, this equation is basically true if x equals 0 or 1, right? And so that's what we call a constraint. And that's how that's one example of how we write logic using math. Maybe we can see another example. How do we write a ternary expression? So x equals, 3 if y equals 1, and 4 if y equals 0. Anybody knows that one? No more pudding.
3 times y plus 4 plus y.
Wait, say that again?
It's like 3 times y plus 4 plus y.
Plus 4 plus y?
Yeah, right? Because it's
So you would have like the result. I don't think that works, but a good idea. Points for effort.
left side.
So, all right, wait, y is 1, you want 3 here, indeed. So I think that part is correct. Plus, what is it? 1 minus y times 4. Is this correct?
Yeah.
Where? Yeah. Up. Everybody convinced? Or did I make a mistake? I think that's correct. Yeah?
Yeah, sorry.
Or if I made a mistake, it's pretty easy to find the correct formula. Is there another example I can give? Maybe something else that's interesting, since we're in the realm of examples for these arithmetic circuits, is how do you prove that a value is in a specific range just using these? That's also an interesting question. So I'll rephrase, like if you have a value x, how do you prove that x is between 0 and 8, let's say? Anybody knows?
I mean, given what?
The what?
Given what?
Well, if you have a value x. Let's say you have a wire x or like a variable. And this variable can take different values in your circuits. But you want to create this, what I call the constraints. You want to enforce that x is between 0 and 8, for example. And that if someone uses a value that's outside of that range, then it doesn't work. Like the constraint is not satisfied. And by the way, at the end, you'll see that we will basically prove a bunch of these constraints. Like the game will be to prove that these are valid, given like some actual values that are taken during the execution. But the yeah. The what?
I mean, it's just driving the solution.
Driving a solution?
Deriving the solutions.
What do you mean?
I mean, it's already a polynomial. You just drive the solutions.
Derive? I'm not sure I get the.
I mean, you just find the solutions if it's a polynomial.
Oh, well, you can find a solution, but here I can use 0 or 1, right? Like 0 or 1 are both valid solution. Maybe to backtrack a bit, when I'm going to prove the execution of a circuit, I'm going to give these values, these variables, values. And I'm going to be able to give this x, I'm going to be able to give the value 3, 4, 5, whatever I want. And so we're going to want to prove that actually, no, in this circuit, it's very important that x is a bit. And so we're going to create these constraints like that to enforce basically that the circuit is correct. And so that's how we enforce that a circuit is correct, is by creating these constraints. And so, yeah.
Are you allowed to use division?
Okay, so actually, maybe that's a good example. So how do we do division? So division is an interesting example. So maybe I'll talk about that first. But yeah, if you want to do like A equals B divided by C, you cannot really do this. And so what you can do is prove that A times C equals B. And that's basically the same. And so usually your constraints will look like that. And you will basically have to compute the results. A is the result. You will have to compute the results in advance and sort of provide it in the circuit. I don't know if that makes sense at this point, but that's something that we call non-deterministic computation, or hints. It's when we can basically input any value in these circuits, but the constraint will make sure that it's correct. So we can do division by doing this. That's the answer.
I guess it's not performant, though.
I mean, there's no other way to do it. Yeah.
But you would like to avoid it as least as possible, normally when writing circuits?
Not necessarily. I mean, it's just, actually here, if you look at that, it's just one constraint. So when we talk about performance, we talk about number of constraints. And so one constraint is totally fine. Yeah.
But can you only use natural numbers?
So we'll see that we're in a field. I guess I didn't mention that. And probably I don't want to mention that because that's a whole other lesson. But you can basically imagine that we're doing this mod P, which is a very large prime number. And I think that's good enough. There was a hand. Yeah.
Is it advantageous to leave it in like without factored, like for example the x1, 3 if y equals 1? Couldn't that just be r equal to 4 minus y?
Wait, say that again?
For the x is 3 if y equals 1, 4 if y equals 0.
Yeah.
Couldn't you just simplify that to r equals 4 minus y? Is it advantageous to leave it in
4 equals
r equals 4 minus y?
r equals 4 minus y? Not sure I...
Wouldn't that work? Like in that example, if you factored out 3y plus 1 minus 4y?
Oh yeah, I mean, I guess you can maybe like simplify that equation. Yeah. Okay, cool. So maybe just to finish, I had this example on like the range of things. So usually, if you want to prove that a value is in between this range, we binary decompose it, and we prove that that it fits into so for yeah. if it's like between 0 and 16, like that it fits in 4 bits or something like that. So maybe I'll just write it up just to finish the example. Up. And then I'll go through R1, CS, and air. And so yeah, imagine that you have x, and so you'll be like x0 plus 2, x1 plus 4, x2, and so on. And depending on the number of coefficients that you allow here, you allow a different range. Does that make sense?
Can you go ahead?
So, like imagine that you had that, for example, and you also say that x0 minus 1 equals 0. Otherwise, we have a bug. Then you know that x is either 0 and 1. Now, if you had that, if you change your constraint and you have that, and same with x1, it's a bit. You have a bit constraint on it. Then you add one more bit, so you have 4 different values, right? So 0, 1, 2, 3. And you can keep extending the range like that. And these are basically variables or wires in your circuit. We have better ways today to do this. This is pretty inefficient.
What's the constraint here?
The what?
What's the constraint on this expression?
That's basically the constraint.
Well, where does it come from?
From my hat. That's just how you can mathematically express that x is a value in this range.
No, I mean computation. Where do these constraints come from? Like, am I adding these arbitrarily?
Okay.
Is it something
Okay.
from the program? Like,
So maybe it's good to explain. Like there's always a compilation process that happens when you produce these circuits, and maybe I'll do a small diagram quickly. But imagine that you have a program here. Then usually what you do is that you pass it to the compiler, and this will give you, let's say, an arithmetic circuit. It doesn't actually give you that. Like these days, it gives you like some other form, but we can pretend that it gives you this arithmetic circuit. Or actually, since I'm talking about constraints, I'm just going to say list of constraints. And this is actually, I mean, it's good that we're talking about that because it's actually a nice way to think about the API here. Once you have the list of constraints, then a prover and a verifier can come and play with this list of constraints that represents the program. But there is always like a sort of a setup phase before with a compiler that gives you this list of constraints. And usually the compilation goes a bit further, but there's what we call a prover key and a verifier key, which are nice pre-computations to sort of speed up the prover and speed up the verifier. But yeah, hopefully that answered the question. But otherwise, maybe we can talk about that after. Oh yeah?
So when you talk about constraints, are you converting the execution trace to a polynomial? And are we trying to find root for that polynomial? Is it the idea here?
So you're jumping, but the idea is that we're going to have an execution trace, which is probably what I should mention next. So that's a good segue. And then at the end, we're going to look at all of these as polynomials and prove that they're equal to 0. So I want to prove that. I want to prove that this identity checks out is the same as proving that this thing is equal to 0. So basically, at the end, we'll have a bunch of equations, and we'll try to make sure that they all equal 0. And I'm not going to talk about how we do it today.
Okay, so, and then the question now becomes finding the roots for this function. Is that the idea? Because making this equal, finding the roots equals making this equal.
Yeah. But you're not going to find any roots. So usually you're going to go through your program, you're going to execute it, and you're going to find values that naturally are roots to these equations. But you're not going to try to solve all of these equations. I mean, you could if you were trying to find a bug, for example. But yeah,
No, I see.
does it make sense?
Yeah, I see, because you're trying to prove the function is low degree.
I feel like we're jumping too much. So no, but we can talk about that at the end if you want.
So this equation is just like an example of a circuit expressed as an equation, right?
Yeah, right. So this is let's say a function in your code that checks that x is in a certain range.
Yeah.
You could think about it like that.
Yeah.
And then you can use this thing for like other things somewhere in your circuits, or you can use the value x somewhere else, and you know. Cool. Okay. I think we should jump to our 1CS air stuff. How much time do I have concretely?
30 minutes.
Okay. Okay. So just to recap, we have a program. We try to create constraints that represent the program. So we want, if the constraints fully represent the program we had in mind, the logic, then we're fine. If it's missing some constraints and it's not exactly describing our program, then we might have some bugs. So it's important to do these steps correctly. And actually, this is why I have a job today, because people don't know how to do it correctly, or it's hard to do it correctly. And we find a lot of bugs in these things. So we get a list of constraints, blah, blah, blah. But these kind of things, we can't really prove that right away. So there is sort of another step to arithmetization, which is to massage the list of constraints and our circuits, however you want to think about it, into something that you can prove. And I mentioned we have R1CS, or air, or Plonkish, or different things. I should probably not talk about too many things, so I'll pick one of them today. And yeah, okay, let me remove this. And I'll talk about, or maybe I can quickly mention R1CS. I think it's good if we end up talking about Plonk and these kind of protocols, which is more like air, arithmetization. But R1CS is pretty easy to think about. So every time how can we do it? So every time you have a new variable in R1CS, you sort of keep track of that new variable in a list of variables. So you can see this as a list of wires in your circuits or list of variables. Variable 1, variable 2, variable 3. Usually we enforce that the first variable is equal to 1 for reasons that I'll explain after. And we also enforce that maybe some variables are known to the verifier. I didn't talk about that, but when you're proving something, there's private inputs, public inputs. And so public inputs is like stuff that the verifier knows. And so here in R1CS, I'll write it here, up. In the representation of R1CS, you end up having the public inputs and the private inputs as values in that vector. Does that make sense, actually? Did I lose someone? All right, well, just imagine that these are variables. Doesn't matter if they're public inputs or private inputs, if that didn't make sense. And so now let's create the circuits in this R1CS form. And so maybe the first thing we want to do is to check if V1 is a bit, let's say. And so, okay, it's kind of tricky to explain actually. But R1CS works by taking a linear combination of these things, then multiplying that with another linear combination of these things, and making sure that it's equal to another linear combination of these things. I don't know if that made sense, but I'll give you the example. Maybe I'll write that also. Linear combination of our witness times linear combination of the same witness. This is our witness. This is it doesn't matter why it's called witness, it's just a vector of values, equals another linear combination over these values. And these values they're not values, they're variables, because we're dealing with a circuit, but when we prove something, they will become values. But now they're just symbolic, they're just variable, and we're just taking linear combination of these. So, okay, I'll ask the question. Can someone tell me how I would verify that V1 is 0 or 1 using these formats? Because I don't know if what I'm saying makes sense, but if someone tells me, yeah. Were you raising your hand or? Oh no. So how can I take a linear combination of these times a linear combination of this equals a linear combination of this to prove that my variable is equal to 0 or 1? How can I do that? And remember, we're trying basically to say V1 times V1 minus 1 equals 0. That's what we're trying. This is equivalent.
One scalar times 0 scalar, and then just check the coefficient.
So here, okay. So this, for this linear combination, you're saying 0 times the scalar 1 there? Or?
Yeah, just multiply the vector by 0.
Yeah, okay, 0. Yep.
And multiply that, and then the second one multiply by 1.
So you want to multiply the whole vector by? So what's the linear combination here of these? So 0 is a valid linear combination, but I need, and actually I don't think that's gonna work. But you can, but okay. So let's scratch that. Oh yeah?
You're skipping in terms of what these rotations mean. Linear combination of what?
Linear combination of the variables in that vector. So you can do like 3 times V1 plus 4 times V3 plus 5. You know.
I mean, it's in doubling, but we're using V, so. And what does this vector represent?
These vectors represent the variables in your circuits. So you could have nothing there, but every time you want to represent a variable in your program, you would create a variable there. And we're talking about the creation of a circuit here, right? The compilation phase. Or the, yeah.
Or are they like scalar linear combinations, or is it like a dot product?
Yeah, scalar linear combination. So like I said, 3 times V2 plus 4 times V3. You can do stuff like that.
You could like dot it with itself and then subtract itself off like previously, but that's not like a linear combination, right? That'd be like
I mean, when you say dotted, you have a multiplication here.
right. Oh.
All right, 20 more seconds.
All the coefficients of everything is just 0, other than V1.
Yeah, you can do that. You can zero all the coefficients, any linear combination, right?
So you could just use that, right? It's just V1. The last,
The what?
the last line that you wrote, you could just use that, assuming that the coefficients of V2, V3, V4 are
Yeah,
0.
okay. So what would be the first linear combination? That's the. I think you're on the right path.
Just
V1, right? So V1 here. What's the second linear combination?
minus 1, 1 minus V1.
1 minus V1. That works. That actually works. And what about the, and here? 0, right? Okay, so I got an answer, so that means I wasn't saying too many bad things. Does that make sense? Here we just have 1 times V1. Here we have a constant and minus 1 times V1. And here we have 0, and we do end up recreating the bit constraint that we wanted to do in the format of R1CS. So that's the the first constraint of R1CS is going to be this 3 linear combination. And so in R1CS, we're just listing, if you look at a circuit in R1CS form, we're just listing 3 linear combinations, a list of 3 linear combinations. Does that make sense? So like a triplet of linear combinations. And it could be another triplet of linear combinations. There could be another triplet of linear combinations. And if there's like 3 triplets of linear combinations like that, we say that, or like 4 of them, we say that our circuit is of size 4. And that's how we can think about performance and these kind of things.
It's always 3 linear combinations.
Yeah, always 3 linear combination, and that's the R1CS. So we say that your constraints are quadratic at most, and that's it. So, oh.
Is this a code to keep it as linear composition of linear combination?
So what do you mean by composition of linear combinations?
Like, is this a goal is to decompose the constraints into linear combination times linear combination times linear combination?
Yeah. Every constraint that we're going to have in our circuit is always going to look like this. Linear combination times another one equals another one. Yeah? Does that?
Is there a logic or a process that you apply to go from that to this? Because I think what we did to count the equation was almost just intuiting. I don't think I can do a process in my head. Is there a process to go from this to this? I'm sure there is. I'm not saying.
So is there a process to find these things? I think at the end of the day, if you look at compilers, like Circom, for example, you will see that they basically write these gadgets. And so like this bit thing is a... Actually, let me backtrack that. In some compilers, they will write gadgets that will do that nicely for you. You don't have to think about it, but the engineers that contribute to the compiler will have to think about. In Circom, you would actually, if you look at the bit stuff in Circom, you would actually see something like that. And the compiler would basically try to fit that into this shape.
Yeah, so is there a process that we are going to talk about, or is that how it's spoken?
Well, I'm not going to talk about that because it's more like implementation detail, but like you can think of an equation. So I think the way Circom works is basically whenever you see additions, it will like queue them up, and I'll explain why. But whenever you see a multiplication, then it will create a constraint. As soon as you see a multiplication, then it creates a constraint. Then after you have ways to like optimize these things. But the reason why you don't create a constraint when you have an addition is because additions are for free. You might have heard about that in R1CS. And why are additions for free? Because you can think of, okay, let's take another color. You can think of like, if you wanted to do V3 equals V2 plus V1 plus V7, like whatever. This thing here is a linear combination, right, by itself. You can do like minus that equals 0. That fits in a linear combination. And you can always fit additions in a single linear combination, so that's why they're for free. Yeah?
So this all runs at the compiler level. And that's all implemented in the compiler.
For most developers, you're not going to see that translation. You're going to write code that maybe looks like this, and the translation to triplets of linear combination is going to be transparent. And there's many ways to optimize these things. So the more transparent it is, or opaque, I'm sorry, the more opaque it is, the better.
Sorry, I didn't get that. How is this addition free again?
So addition is free. So here I did an addition, right? I said V3 has to be equal to V2 plus V1 plus V7. And you can keep adding stuff. You can see that it's always going to fit in one linear combination. Does that make sense? Like you don't need to reduce. Maybe to take another example, if you had like V7 equals V6 times V5 times V4, for example, you would first have to do let's say V8 equals V6 times V5, and then you would be able to do V7 equals V8 times V4. You would have to like cut your multiplication into two constraints. Like that you can write as a triplet of linear combination, and this you can write, yeah? Yeah?
I've heard that you can't express anything more than quadratic.
Yeah, so that's basically why whenever I have something like that, like I need to cut it. I need to reduce parts of my equation, of my circuit or my program to like one constraint, and then I can use the results in another constraint.
So that would be like two arithmetic circuits.
These are part of the same circuit. They're just two constraints that are part of the same circuit.
So if you satisfy those constraints, you could...
That's your circuit, right? You could think of like my circuit is this thing. It consists of these two constraints. And anybody who wants to prove an execution of that circuit with actual values instead of these variables will have to prove that these two constraints check. And again, I'm not going to say how you prove that. Are you raising your hand? Or?
Sort of. If other people have questions, please go ahead. I guess not. So, why can it be represented this way?
Why can I represent what?
Why can this be represented in this way?
This one?
The linear combination, the product of two linear combinations of the equal another linear combination. That way, okay, I get where the quadratic part comes from. Well, what's the guarantee that the vector, I don't know what's stored in the vector, except variables in the arithmetic circuit. I don't know where they come from, but what guarantees that it could be represented in this way? Like, this is an example of
the bit constraint, or
actually a cubic function. Well, why can it be? What guarantees that it can only be quadratic? It can go up to quadratic.
Just trust me, bro. Like that's gonna be my answer. It's like basically any type of logic can be like encoded as an R1CS circuit. And okay, you don't have to trust me, but if you want, you can read more about it. But
if there's like one theorem that's like proves it, it's like I'm okay with that.
Yeah, it's for now. Just trust me. You can encode any of these circuits, arithmetic circuits, as these triplets, and just do that. Take as many as you need, but you will be able to encode any arithmetic circuits in this form. All right. Did you have a question or no? All right. So maybe I do want to mention air because it is interesting and it's sort of the basis for a bunch of other schemes. Maybe before jumping to air, I just want to emphasize that there's a compilation phase where you get a circuit, but the values are symbolic. They're just variables. They haven't taken any values yet. And then there's a runtime phase when you're proving the execution of something. You actually put values in these guys. And there's a process of proving that these constraints are correct given actual values. And that's the stuff I'm not going to talk about, but just create this distinction in your head. We're only talking about the first part, creating symbolic circuits. Okay, so no more R1CS, that's enough. And now we're going to look at air. And I'm not sure how I'm going to introduce that. Okay, so we're going to look, so in R1CS, there was like, you mentioned execution trace earlier. In R1CS, there was like one execution trace. It's like our witness vector. You can think of it as like some sort of single execution trace. In air, you can think of, you have to see things as a table. And actually, this is very helpful. Everything in these schemes can be seen as tables, and the sooner you see things as tables, the easier it is, or at least to me. And in this table, you're going to say that each row, actually each column, is some sort of register. So let's say register 0, register 1, register 2, register 3. These registers, like a CPU, can take values. And if you only look at this, you have the values in the registers at some point in time. When you're going to execute your circuit, you're basically going to sort of record the values of these registers at different point in time, and you're going to have different rows. And so this is how you can think about this air thing. Oop. You can think of it as an execution trace where you're recording the values of registers at different point in time. And the size of this table, the number of rows you have in this table, is basically the size of your circuit. Does that make any sense what I said? Yeah.
Do the columns correspond to like left and right wires?
So they can, for example. So you could say, so the air arithmetization, I don't remember what it stands for, but basically says you can do whatever constraints you want.
Is the table ever like wider than 4?
Yeah. So actually in Plonk, there's only 3 columns or wires or registers, but you're not necessarily, or like vanilla Plonk, the original scheme, but you don't necessarily have to stop here. Like for example, Plonky had like hundreds of...
So it's just like extending out the left-hand side of the RLCS, almost? Not really.
Not really. I'll give you another way to think about it. You can think of each row as a gate. And basically, if you have 3 variables, so R0, R1, and R2, you can see these as gates with 2 fan-in and 1 fan-out. So exactly like the gates that we're used to, where, for example, R0 could be the left wire, R1 is the right wire, and R2 is the output wire. And if you increase the number of registers or columns, you can think of sort of adding inputs or adding outputs to your gate.
Gotcha. That makes sense.
So again, you can think of whatever is here as symbolic variables. And when you want to prove something, these will actually take values. And you will try to constrain how these values, what values you can have there. So, okay, so in air, maybe we can still use the bit constraints, but this gate could be like the bit constraint gate, and you could have sort of the constraint that R0, or actually that's not is it a good? Actually, let me use a very simple gate. I'm going to do an addition gate. You could say R0 plus R1 equals R2. I don't know why I didn't use that gate earlier, because that's easier. So you could, in these air things, if you create a constraint like that, it's basically going to get applied to all of the rows. We're not in the R1CS thing where every constraint can be different. Here, every time you add a constraint into your circuit, it's going to apply to all of the rows. Does that make sense? So if I had a bit constraint, it kind of sucks because then my circuit is only going to be about bit constraints. So air gives you one more thing. Well, it gives you a few more things, but another thing that's interesting is that you want to like link the output of these gates to maybe the input of these gates. Like you want to like wire the output of gates to the input of other gates or these kind of things. So air allows you to also, in your constraints, involve the next row. Or even the next row. But I'm just going to take the example of constraints that apply to two consecutive rows all the time. So here, for example, we could say that R2 is going to be on the next row, next R2. So it's like, if you have like 7 and 3 here, then you would have a 10 here. Or you would be forced to have a 10 there. And if you don't have a 10 there, then you wouldn't be able to create a proof the verifier wouldn't accept that. So that's it's sort of the basics of AIR. And just to recap, you can have multiple registers. Every row is a point in time in your execution, and you can sort of link rows, or if you see them as gates, you can link gates or the wires of gates together by having constraints that apply to 2 consecutive rows. And if you have a constraint, it applies to all of the rows in your circuit. Okay, these are, I think, the 3 things, or I think that was 3 things. Does that make sense?
Yeah.
You said no, or?
Yeah.
Yeah?
Is this the witness now, the equivalent of the witness from the RMCS example that we talked about? So are we, or is it the proof itself?
So your witness, so the witness are the runtime values, right, that you take when you execute the actual circuits, are going to be this table. Basically, your witness is going to be this table with actual values.
And what is the advantage we are having in this representation over the
Over R1CS, or?
It feels more complex in the sense that there's a constraint that needs to be applied to like all the rows, which.
So there's different things which are nice with this representation. The first thing is that you're not limited to quadratic constraints. You can have much more complex equations for just one gate. And another thing is, because you're applying the same constraints on all of the 2 consecutive rows, you have very efficient schemes, like, for example, Starks. So, maybe I should mention that Starks are basically based on AIR. And so Starks are, one of the reasons why Starks are so efficient is that you have the same constraints that apply to everything. And usually these constraints is a bit more complicated because you have to take different edge cases and
how is like R1CS and AIR stored on a computer?
Say that again?
Like how is R1CS and AIR stored on the computer?
It doesn't matter. It's like implementation detail, but you could be like, and usually this is what we do, like this is an array or a vector, this is a vector, this is a vector. And if we're talking about the witness, this is the vector values in our field, vector values in our field, and so on. Or if we're talking about a circuit, then you would not store anything here, but you would store the constraints. Because these things wouldn't have value yet. Yeah?
How can you verify that those vectors aren't temporary?
So I'm not going to say anything about that, because basically that's how can you verify that the prover is not cheating with these values is kind of the same question. And that comes in like, that's outside of the arithmetization topic, which is how do you prove these actual constraints? How do you prove these relations, right? But yeah.
So I guess like in R1CS, the constraints you can represent as like these like coefficient matrices or whatever. In here,
Exactly.
how do you represent constraints?
Since it's the same constraint that applies everywhere, then you just write it, you store the equation somewhere. So one way to do it is you could have like a symbolic language where you have a name for different variables and then you compose them. But it's pretty implementation detail. Like it's not, I guess it's not too important to understand like what I'm saying here. Yeah?
Does Plonk work with tables wider than 3? Because like there's only 2 wires in Plonk.
Yeah, so as I said, like so Plonky came out a while ago, but they had like 100 something columns.
Right.
So the protocol I used to work on had like 15 of them. So different protocols will choose different trade-offs.
Uses Plonk in the backend.
Yeah.
It's not like the Plonk equation or whatever, right? It's like it only has left and right wires and alpha wire.
Right.
If those rows correspond to like more wires coming in, does that mean you have to change the Plonk equation?
Yeah, so Plonk has like, so I guess I haven't really been talking about Plonk so far, so maybe I should talk about Plonk. And and I'll try to answer that question. But okay, so how do we go from air to Plonk? To Plonkish, let's call it. That's what people call it these days. And so Plonk says, okay, we're gonna use the same stuff as air. We can do exactly the same thing. We can have like a get that applies everywhere, or a constraint that applies everywhere. We have our registers, whatever. Every constraint applies on 2 consecutive rows, okay? But we're gonna give you more power. We're also gonna add like a permutation primitive, or what they call copy constraint. Maybe I'll write it here. Copy constraints. And that's quite powerful. That basically allows you to link stuff, across your table. And so you can sort of arbitrarily say, oh, this register here at this time is going to be wired to this register here at this time. And you can just create wires like that across your table. So that's one of the major differences or the major upgrade from air to Plonkish, is that you have access to this permutation or copy constraint thing. The other thing that we're going to add is a way to have different constraints depending on the row you're at. And so the way they do it in Plonk is that they're going to have a bigger table. They're going to extend that table. And this table is called the selectors. And same size. And you're going to say, if this is 1, then you apply the first gate to this row. If this is 1 here, then you apply the second gate to this row. And usually it looks like that. You either apply one gate or constraint, but it's either or. So yeah, does that make sense? Like the 2 big differences of Plonk, again, are that we have access to this copy constraint or permutation primitive, where you can wire stuff across the board. Very powerful. And we also have access to these selectors that allow us to choose which constraint we apply to different rows. And we can have, vanilla Plonk has like 5 of them, I think, and you can have like much more. Yeah. And so the question was,
I guess I have 2 now. The first one is like if the columns correspond to wires coming into the gate. Like the original Plonk equation only has like 2 wires, left and right. So to like more, does that have to change?
So yeah, you'd create a gate that can take way more stuff.
You add Q0, Q1, Q2, like additional selectors.
Right. So you'd create a new selector for like a constraint that takes much more registers, and would make use of all of these registers that you have.
And my last one is, I missed it. Why is it that the constraints, the gates apply to every row?
So why do the, say that again?
You said the constraints apply to every row.
Mm-hmm.
I must have missed why.
There is no reason why. It's just the way Starks makes use of this arithmetization or Plonk, or like they work this way. So this is kind of a hack in Plonk, so that you can apply different constraints to different rows. But yeah, this is the way it is, basically. And by the way, I'm probably going to stop here. For Plonk, I think I said all of the stuff I really wanted to say. So yeah, I'd say at this point it's good to ask me questions if you want me to clarify that. Maybe one last thing I can say is that these selectors are pre-computed. They are known based on the circuit that you want to have, based on your logic. You're going to hard-code these things in the compilation phase. Whereas Starks uses this air stuff, and so doesn't have access to that, and so they have to do it a bit differently. But yeah, this is one of the reasons why Plonk is so efficient, is that you can pre-compute a bunch of these stuff. And yeah. Question? Yeah.
Like an easy example of like some sort of computation that is like well suited for air versus non-CS.
So, like for example, usually you're going to use these things to, if you have like complicated constraints, for example, for hash functions or elliptic curve operations or these kind of things, without nice constraints of like higher degrees, you would have to create a lot of constraints to just add two elliptic curve points together, or like do one hash function, or something like that. For example, it could take you like thousands of constraints to just hash something. But I remember like Plonky did like one row, so like one row, so one constraint for one hash. So you can really do like amazing stuff thanks to that. It comes with a trade-off, but yeah. Does that make sense? Yeah.
I think as like whenever there's like an ending note, like taking just like call it like a dummy function and like walking it through, like it gets flattened into like the gates, right? Which are then the gates of like the circuit, which represents the evaluation of the polynomial, which is then the like constraint system, which is like the system of equations that has to be like just like tying it all together with like a theoretical example of what's happening might be helpful. I don't know if that's easy to do like on paper.
Yeah, I'm trying to think of a. I mean, you're talking.
I actually read a case where someone tried to use Fibonacci sequence as a way to do it, but when it comes to the combination with circuit thing, it would be a lot more complex.
The combination with what?
I mean, if you combine the kind of Fibonacci sequence with the circuit side of things, the logic gates or these kind of things, the thing will be a lot more complex. I mean, there are some people trying to do some simpler explanation with one simple example.
Yeah, so I don't know if that's gonna maybe help, like, or address both of these. But what I can do is give an example of because I haven't really done that, but I can give an example of a gate in Plonk, and you can see how you can use that gate to do like additions and multiplications, and like how a circuit would get compiled to that. And you tell me if you have more questions after. Okay, so let me do that, and hopefully it will make sense. Okay, so the vanilla gate in Plonk, like the way this works, I said there's like 5 of them, and the big constraints that get applied to every row in Plonk is, okay, I'll make some space. It looks like QL, that's a selector. What can I call these? Times R0, or I'll call that left. So imagine that this is RL or something like that, plus QR times RR plus QO times R0 plus QM times RL times RR plus QC. So, okay, if you don't know about Plonk, this is actually one of the most important things about Plonk. So it's good to know. This is what I call the vanilla gate. That's the main gate of Plonk in the main paper. And this allows you to do addition, multiplication, and addition with constants, multiplication with constants, and so on. And so you can see that this thing, actually Plonk by default doesn't use this thing where constraints apply to like two consecutive rows, because they don't really need it because of the permutation, or they decided not to use it. And so they just have one gate that just allows you to do an addition or multiplication and so on. I can explain exactly how this works, but okay, I'll ask you a question. How would you add 2 registers? Like imagine that you want to add the register, I'll rename these actually, it's gonna be easier. And R3 doesn't exist in vanilla Plonk. RL, RR, RO for output, right and left. How do you create, or how can you give values to your selectors so that you can add RL and RR into RO? So that you can have RO equals RL plus RR, right? So we want to do an addition. We want to do an addition on the first row. And the only thing we can do when we compile the circuits is to choose to hard-code values for all of these selectors. Does my question make sense? So what's the answer then? What value should we give to this selector on the first row?
1.
So we'll give it 1, okay? This QL here. 1, 1, minus 1. 0, 0. Yes, good job. Does that make sense for everyone? How would I do a multiplication here? Someone else answer. How would I use these selectors to do a multiplication? So let's say I want to do a multiplication on the next row. Oh. All right, we only have one good student here.
0, 0, negative 1, is it 1, 0?
Are you sure? It looks good to me, but so yeah, and you can imagine like if we wanted to do like, actually that's interesting also, like what if we wanted to do 3 times RL equals 0. Okay, last question, I promise. Maybe someone else answer that. Hmm.
3, 0, 0, 0, 0, 0.
Yeah, pretty much, yeah. Cool. Yeah, that was long.
No.